Thank you very much for the introduction. It's a pleasure for me to be here today, at least virtually. Let me share my screen. I hope the sound in the room is okay.
It's excellent. Yes.
Okay. Good. So let me get a pointer out here. Good. So I'll be talking about polarization, and this is a little scary because there are a number of people in the room in Cornell here who know more about polarization than I do, because I'm a relative newcomer to this field. But in the process of kind of joining this field, I learned some things that I thought would be useful to share with all of you. So over the years, a number of people have been involved in this. I particularly want to acknowledge Cyrus Dreyer, who was a graduate student in my group. He is now on the faculty of Stony Brook University. Current people in my group include Hao-Chen Wang and Akash Ram. And then I've also collaborated with my long-term collaborator, Jörg Neugebauer, on this, as well as with experimentalists such as Simon Fichtner and of course, the various scientists at Cornell who are acknowledged here. The work has been funded through several sources, most recently by the Supreme Center. So, polarization. I'm going to be focusing on nitride semiconductors. The traditional nitride semiconductors have the Wurtzite structure. That structure has sufficiently low symmetry that it can have spontaneous polarization oriented along the z-axis, 0, 0, 0, 1. And of course, as in most of these low symmetry materials, you can also have piezoelectric polarization, which is going to manifest if a strain is present in the material. And of course, in the nitrides, we have strains because we make heterojunctions. And because of the lattice mismatch, strain will be present in the thin layers that are formed at these interfaces. So that's the basic principle that's well known. And you can write down an expression for the polarization in a specific material that says it's the sum of the spontaneous polarization plus these terms due to piezoelectric polarization when you have strains epsilon1, epsilon2, and epsilon3. So the third axis is always implicitly assumed to be along the z-axis. So obviously, knowing these various coefficients, the spontaneous polarization, as well as the piezoelectric coefficients, is very important when you want to do any analysis or design of these nitride devices. Why is it important? Well, it's very important in light emitters where you squeeze a thin layer of indium gallium nitride in between thicker gallium nitride layers. So you have a polarization discontinuity at these interfaces due to the difference in spontaneous polarization between indium gallium nitride and gallium nitride, and due to the piezoelectric contributions. And that polarization discontinuity leads to a bound charge, which then in turn leads to electric fields. And in LEDs, we don't like the presence of those fields because, as you can imagine, it means that they will make electrons go to one side of the well and holes to the other side of the well, and that will reduce the radiative recombination efficiency. So in the context of LEDs, you want to understand these fields, but kind of from the point of view of controlling them and maybe even getting rid of them. In transistors, in electronic devices, it's a bit of the opposite. There, the polarization fields are actually beneficial and functional because due to the fact that you now have a thin layer of, for instance, argon on top of gallium nitride, you again have a polarization field, and that polarization field actually helps you confine electrons at the interface between argon and GaN, and that gives you the sheet density of electrons that you control in a transistor to get all the functionality. So again, knowing the polarization on the gallium nitride side and the aluminum gallium nitride side lets you determine the polarization, discontinuity, and to some approximation that then gives you a density of two-dimensional electron gas. So, as I already said, you need to know the various constants that go into the formulas to do device analysis and simulations. This is just a random example from one of the papers we published on this some years ago, and actually in the process of doing these simulations, we simply took the values of the constants as they had been published in the 1990s without further analysis. I'll come back to that in a few minutes. So I motivated the need to know polarization properties in the context of the traditional devices, but starting about 5 years ago, based on research that was done 15 years ago, aluminum scandium nitride alloys have actually come to the forefront as a new member of the nitride family with very exciting properties. The piezoelectric constants in this alloy are much enhanced relative to aluminum nitride, which makes them very attractive for devices such as radio frequency filters. And actually that is already a commercial product because the benefits of using this alloy over the traditional aluminum nitride are outstanding. In addition, because of getting a larger polarization discontinuity, you can also employ these alloys in transistor structures and hopefully get larger interfacial carrier densities, so very beneficial for transistors. Even more exciting is that these alloys exhibit ferroelectricity. When we usually think about nitride semiconductors, we don't think of them as being switchable. We know they have a spontaneous polarization, and traditionally we have thought of that polarization as being fixed along a particular direction, say the plus C direction, a gallium polar direction. Until 2019, it didn't really occur to anybody, I think, to try and switch this polarization by applying an electric field, as you would in a ferroelectric. But in 2019, Simon Fichtner in Kiel in Germany demonstrated that you can actually switch the polarization of an aluminum scandium nitride alloy. These are the loops that he observed for various concentrations of scandium in the alloy, and he measured large values of polarization. So this is extremely exciting because you can now envision all kinds of applications, ferroelectric transistors in which the ferroelectric is integrated as a gate dielectric, but also, of course, in the context of ferroelectrics, memory type devices where you can integrate computation with memory cells. You can do this with this material with low power, you can do it with high speed, and people are very excited about the prospects of applications in AI and machine learning because this sort of integration allows you processing of real-time data with minimal latency. Also aluminum scandium nitride seems to be relatively easily integrable with silicon, which of course is very important in the context of silicon technology, and hence there is a lot of excitement about these various big data applications. On top of all of this, aluminum scandium nitride also has other excellent properties in terms of dielectric permittivity and nonlinear optical properties. I will not be talking about those today because we're going to focus on polarization. So I'm a theorist, and we need equations and methodologies to be able to say something useful about quantities such as polarization. And interestingly, polarization was a subject that was really not well understood for many, many years, even though phenomenologically it was observed and well characterized. Now, the reason for this, I'll just kind of try to explain by waving my hands. The reason is that piezoelectric polarization is kind of relatively easy to formulate, but spontaneous polarization has a problem. In a finite system, a molecule or something like that, if you have charges, plus charges and minus charges at some position in this molecule, you can easily write down what the dipole is that corresponds to those charges. It's basically, as you all know from elementary electrostatic courses, it's charge times distance summed over the various charges that are present. So that works perfectly well in a finite system, and it immediately gives you the polarization. But in a solid, you cannot quite do that. And one way of thinking about this, which you can easily convince yourself of when you just write it down on a piece of paper, is that because of the periodicity, when we describe a solid, we need to choose a unit cell that is going to be periodically repeated and is filling up all of space. And it turns out that the value of polarization that you would calculate in this naive way depends on the choice of unit cell. So you don't really know what the right value to use is. So this situation was addressed in 1993 in this seminal paper by King, Smith, and Vanderbilt. And in parallel, there were also papers by Raffaele Resta that addressed the same issue. And this approach has become known as the modern theory of polarization. And this is about the only complicated equation I'm going to be showing in this talk. The polarization can be expressed within this theory as a sum over ionic contributions, which are kind of these point charges I was talking about earlier. So if you think of a gallium atom, all of the action usually is with the valence electrons. So you basically have an ionic charge of +3, and calculating polarization associated with that, you do in the way that I was describing in the hand waving approach. But then the contribution due to the electrons, you need to carefully think through. And this expression is actually related to the so-called Berry phase approach, which interestingly also comes up when you try to calculate emerging materials like topological insulators, and you want to calculate invariance, etc. It's the same sort of integration over the properties of the electrons in the reciprocal space. You integrate over the Brillouin zone. That determines the electronic contribution to the polarization. So this is complicated, but it's well under control by now because we can do first principles calculations based on density functional theory using various types of codes that accurately give us the wave functions that enter into this expression. We can evaluate this expression and we get the polarization. Okay, so in principle, that should be the end of the story. We can calculate this accurately. However, a problem has emerged. And so the first part of my talk after this motivation will be devoted to the fact that there is confusion over the magnitude and even the sign of polarization in nitrides. Okay, so for those of you who already know this, I'll try to explain why and set things straight. For those of you to whom this is new, let me sketch the situation. Okay. So I talked about this modern theory of polarization and the problem of like uniquely defining a polarization. And what became evident from these seminal papers is that you can really never define an absolute magnitude of the polarization related to the problem I outlined before, the periodic nature of a solid. But what you can do is define polarization as a difference between values of so-called formal polarization. So the equation that I showed on the previous slide essentially gives you a quantity that is the formal polarization. And then to obtain a quantity that is relevant for a particular material or device structure, you will need to take differences. Okay, in the context of piezoelectric polarization, this is kind of obvious and implicit because the reference clearly is the unstrained material. When we evaluate the piezoelectric polarization, we're calculating what happens when you apply strain. So you compare with the unstrained material. So piezoelectric polarization, no problem. For spontaneous polarization, however, if you just take a material by itself, it's not clear a priori what the reference should be. At an interface, things are still clear, right? I showed you the example of aluminum gallium nitride on gallium nitride before. So in principle, we should be able to calculate the formal polarization for aluminum gallium nitride, the formal polarization for gallium nitride, subtract those two if we have calculated them consistently, which I will come back to, but subtracting those two values should give you the polarization discontinuity that we are interested in. But of course, when trying to do device simulations, we don't want to be forced to do a complete first principles calculation always for the complete heterojunction. What we would want is to have one value of spontaneous polarization for gallium nitride, another one for maybe not aluminum gallium nitride, but say aluminum nitride, and then you get values for alloys by interpolation, but we have a value for each bulk material. We subtract those two. We want that quantity to give us the polarization discontinuity. So we would like to define a value that is associated with a single material, okay? So how do we do that? As I said, since polarization is really only defined in terms of a difference for the single material we are focusing on, we need to choose a reference structure. So this effective value of the spontaneous polarization would be a difference between the formal polarization for our Wurtzite structure of interest and a reference structure. What do you choose for the reference structure? In ferroelectrics, where originally most of the applications were, the choice is obvious. Because in ferroelectrics, you switch the polarization. You switch it from, say, a value plus P to a value minus P. And in the process of doing that, you go through zero, okay? So what you know is that the total change in polarization will be 2 times P. And the reference structure is the one that you go through along the path of switching the polarization. So it's going to be a mirror symmetric state that has zero polarization. In Wurtzite structure nitrides, that reference would therefore be the layered hexagonal structure, okay, which is illustrated here. So on the left is the Wurtzite structure. Schematically, I'm just showing one chain of atoms. And those of you familiar with the Wurtzites know that we define this parameter U, which expresses the length of the bond between, say, gallium and nitrogen relative to the C lattice constant, okay? And in an ideal Wurtzite, you would have a value of U that is equal to 3/8. But of course, there is flexibility for the atoms to move along the C direction. And they actually, this is the value for aluminum nitride, they settle in a position where U is equal to 0.382. Well characterized experimentally, and this also comes out of calculations. So what do we want to do when we switch the polarization? Well, as is illustrated schematically here, for instance, if you leave the aluminum atoms in place, you start moving the nitrogen atoms towards the plane of the aluminum atoms, and at some point, nitrogens and aluminums will be in the same plane, and your polarization will be 0 because you now have mirror symmetric structure that macroscopically will have 0 polarization. And then, of course, if you would keep going in the switch, you would ultimately switch the polarization and have it pointing along the -C direction instead of the +C direction. So this is well within what is accepted for the ferroelectrics. And so we should choose this layered hexagonal structure as our reference. By the way, this is not some hypothetical structure. A number of materials have this structure. Most famous example, hexagonal boron nitride, which is kind of the graphite equivalent of the three nitrides. It has boron and nitrogen atoms sitting in this layer. Okay, so for aluminum nitride, for instance, we want to choose this reference as this structure as our reference. And then in the context of the sort of calculations that I described to you, we can actually map out what the formal polarization is as a function of the U parameter. So the point at U equal 0.5 corresponds to the layered hexagonal structure. That's where the formal polarization is 0. And then if we change U, all of these calculations, all of these points here are explicit calculations for the polarization as a function of U. By the time we get to the value in aluminum nitride, 0.382, we have the Wurtzite structure, and we have this value of the polarization, roughly 1.3 coulombs per square meter, a large value, okay? And then if we want to talk about the value of the spontaneous polarization for aluminum nitride, in the context of this approach, it makes perfect sense that we choose the layered hexagonal structure with 0 polarization as the reference, and we say that this value here is the appropriate value for aluminum nitride referenced to the hexagonal layered structure. Okay. So can we confirm this? And yes, now that we know that nitrides can be switched, can be ferroelectric, we can explicitly verify this. Now, aluminum nitride itself is still really hard to switch, although as you can see in the plot on the upper right here, there have been experiments in which this is demonstrated, but it's usually aluminum nitride that is not particularly good quality. But I told you aluminum scandium nitride is switchable, specific values are available, and so we should be able to compare our calculated numbers with these measured numbers, okay? And you can already see in this plot here that indeed this value of about 130 coulombs per square meter seems to be also what comes out of the measurements. And you can do that calculation, that comparison more accurately. So this is just kind of to drive the point home. I told you about, you start with an aluminum polar structure, you start switching, you drive the anions into the plane of the cations, you get your layered hexagonal structure, and then if you keep going, you would switch the polarization, and basically these extreme values of the polarization is what you should measure in the experiment, and there is essentially perfect agreement between our calculated numbers for this material and the measured numbers. Okay, so that's very reassuring. We seem to be doing the right thing when we are calculating the polarization. However, when Simon Fichtner and others started publishing these results, there was a lot of pushback in the field because the numbers they were measuring did not agree at all with what people in the traditional nitride field were expecting. So now I want to try and explain why that is. There was confusion about both the sign and the magnitude of the polarization. Why was there confusion? Because of a convention that is unique to the nitride semiconductor field of choosing a different reference for the spontaneous polarization. I told you that in the context of ferroelectrics, it's perfectly natural to choose the hexagonal layered structure as your reference. But that was not what was done in the field of nitrides, and sadly, it is still, by and large, not what is done. Instead, the reference structure has been chosen to be zinc blende. Okay. Now you may wonder, why choose zinc blende as a reference structure? Well, this goes back to this seminal paper published in 1997 by Bernardini, Fiorentini, and Vanderbilt. This is the same David Vanderbilt who developed the modern theory of polarization. So he clearly knew how to do this correctly. And they calculated values that since then have basically been implemented in all the analysis and device simulations that people have done for nitrides. Now, why did they choose zinc blende? They chose zinc blende because, first of all, they were not thinking of ferroelectric properties, because at the time it didn't occur to anybody that you could ever switch the polarization in a material like aluminum nitride. So they tried to pick a more relevant reference structure. And well, we know the zinc blende structure is really not that different from the Wurtzite structure. If you think of stacking along the C axis, the equivalent being the 1-1-1 axis in zinc blende, in Wurtzite you have an AB type of stacking. In zinc blende you have ABC. But locally, the type of bonding is very similar. The atoms are tetrahedrally coordinated, and you can explicitly construct an interface between Wurtzite and zinc blende, which is actually a prerequisite in the modern theory of polarization to be able to define a polarization difference meaningfully. So they basically figured that zinc blende was a good choice. On top of that, zinc blende, as we know, macroscopically does not have a observable spontaneous polarization, right? Unlike Wurtzite, where clearly spontaneous polarization is present, the symmetry of zinc blende is higher, and that actually implies that the spontaneous polarization on a macroscopic piece of zinc blende material will be zero. So that seemed like another reason why this was a good choice as a reference structure. Unfortunately, this issue of the spontaneous polarization being zero is true at the macroscopic level, but it's not true for the formal polarization of zinc blende. So if you use that formula that I showed to you for calculating formal polarizations rigorously, and you apply it to a zinc blende structure, you find a non-zero value. Now, people are often confused by this. They say, well, how is it possible that you can find a non-zero formal polarization for a material that macroscopically doesn't exhibit any polarization? The reason, again, goes back to this more complicated way in which we need to define polarization. It's not a unique value. And without going into the math, I can tell you that formal polarization is only defined modulo a so-called quantum of polarization. So it's not a unique value. There is basically a range of values. So as long as the formal polarization exhibits all of the symmetry properties associated with a particular crystal, it is a perfectly correct value. So the formal polarization can be non-zero, but if you apply a symmetry operations, such as doing mirror symmetry on your crystal, and you find a different value of the formal polarization that is still the same within modulo the quantum of polarization, everything is fine. So that's the case for zinc blende. Bottom line being, formal polarization is non-zero. Okay, so intrinsically, that's not really a problem, because I already told you, anytime we talk about polarization, we should be talking about a polarization difference. And well, if you choose zinc blende as a reference and your polarization of zinc blende, the formal polarization is non-zero, you just have to take that into account, okay? And if you do that, there shouldn't be any problem. Previously, I showed you what you get with the choice of the hexagonal layered structure. It was this large value, 1.3 coulombs per square meter. If you choose the zinc blende reference, because the zinc blende reference actually has a non-zero formal polarization, you're going to get a different value. So unfortunately, my plot of polarization versus U disappeared, and only the values that I wanted to highlight are shown here, but they actually suffice to make the point. U equal 0.382 gives us a value of the polarization, the formal polarization, that is going to be referenced to the layered hexagonal structure, and that's this very large value. The formal polarization of zinc blende, I schematically put in this plot, which isn't showing up. This formal polarization of zinc blende turns out to be actually slightly higher than the formal polarization of Wurtzite. So if we choose zinc blende as the reference structure, we're going to get a different sign of the spontaneous polarization. And we're going to get a different magnitude, because zinc blende and Wurtzite in magnitude don't differ that much less than the difference with the layered hexagonal structure. So you're going to get a much smaller magnitude. Instead of 1.3 something, you get minus 0.09, like 2 orders of magnitude smaller. Okay, so this is why there has been understandably confusion, because in the field of nitrides, people have implicitly used the zinc blende reference. And if you use those values, you obtain very different magnitudes and signs of polarization differences.
Hey, Chris, I want to ask a question.
Sure.
Okay. So from the modern theory of polarization, you said that the polarization itself can be several values with some modulo. And my question is zero a possibility for the zinc blend with that modulo?
It's a possibility, but it's not what you get when you evaluate the value, okay? And this is an exercise that I'll pose as a homework problem. Because in the case of zinc blend, it actually turns out that the electronic terms integrate to zero, okay? If they didn't, I wouldn't assign it as a homework problem. But the homework problem that you can easily do is take this expression here and apply it to zinc blend, okay? And you will immediately convince yourself that you do not get zero, not for any choice of the origin of your unit cell, okay? You will always get a finite value. Unlike, for instance, the case of the hexagonal layered structure, where evaluating this quantity does give you zero, okay? So while in principle it's possible for any structure to have a formal polarization of zero, it's not true for zinc blend. And it's easily verified that it is actually a finite value. I hope that answers your question.
Well, sort of. But how do you decide which unit cell to choose? Because you said you could choose different unit cells and get different values, but you're saying that there's one value, the one that you have on this plot. Which unit cell did you choose, and how is that the right one?
It's the right one because since the polarization is multi-valued, in principle, there isn't just a single value here. There is this replication of values modulo the quantum of polarization. So you are asking an excellent question. Which one out of this array of values do I choose? I choose the one that is on the same so-called branch of polarization as my reference structure. And this is actually why we make these plots, not just for illustrative purposes, but to make sure that as we gradually change the structure from Wurtzite to layered hexagonal, we stay on the same branch of the polarization. And since for layered hexagonal, we know macroscopically that this value gives us zero polarization, this assures us that this calculated value is the correct one to use for aluminum nitride.
Thank you.
Okay, so as I said, if we carefully keep track of what's chosen as the reference structure, there should not be a problem, even if you choose zinc blend. Okay. Now, as I said before, in the case of the layered hexagonal structure, things are simple because our polarization for the reference structure is zero. So we can just use the formal polarizations, for instance, of gallium nitride and aluminum nitride, if that's the interface we're interested in, and just subtract those two polarization values, formal polarization values, and we get our polarization discontinuity. In the case of zinc blend reference, we can use the same expression, but we need to take our polarization of our reference structure into account. And these polarizations for zinc blend are non-zero, okay? And as you can see in this plot here, where I've now added in the orange dots the values for gallium nitride, the formal polarization of aluminum nitride and gallium nitride is different for Wurtzite, but it actually is also different for the zinc blend structure. So these terms that enter because of our choice of reference structure are non-zero, and they would need to be taken into account anytime you do a calculation of a polarization discontinuity if you choose the zinc blende as the reference. Okay. And the sad thing is that this has not been done. And as far as I know, even in the device simulation tools that we are using to date, this is still not correctly implemented. Now, I think I already hear some of you thinking, well, why hasn't anybody noticed this? Okay, so let me try and address this. I told you that the polarization, the spontaneous polarization values calculated for the hexagonal reference structure are very different from the ones for zinc blende. The example of aluminum nitride is what I showed, 1.35 reference to hexagonal, minus 0.09 referenced to zinc blende. Okay, so these are huge differences, and this is true for each of the nitrides. And then you can say, well, we calculate these polarization discontinuities, and they're going to give different values. In fact, very different values. Reference to the hexagonal layered structure, the polarization discontinuity for gallium nitride, aluminum nitride is minus 0.039. Reference to zinc blende, using these values, it would be plus 0.055. So we get a totally different value with a different sign. I was trying to convince you that the values in green are the correct ones that we should be using. People have been using the ones in red on the right, but it's not possible that both of them are correct. So what's going on here? Have I been trying to fool you by saying, oh, you should be using the layered hexagonal structure? Well, the answer to this is that sadly, a second error has been made in the thousands upon thousands of simulations that have been done since 1997. Okay, so bear with me and I'll try to explain this second error, because I think for all of us who are interested in using these materials, it's really important to get these things straight. So far, I only talked about spontaneous polarization, but clearly, because there is a lattice mismatch at the interfaces of interest, there is a strain and there is a piezoelectric polarization. In the introduction, I told you, oh, we all know how to calculate piezoelectric polarization. Sure, we know what the correct expressions are. But what is less well known is that there are two types of piezoelectric constants. They depend on the electrostatic boundary conditions. One set of polarization constants corresponds to null electric field, essentially a short-circuited condition. And that's what you would get if you kind of naively do the experiment of, like, you have a freestanding material, you strain it by pushing on it, and you try to measure what the polarization is, which is typically done by measuring how much current flows as a result of the fields and charges that are being generated. So those are the proper piezoelectric constants. But those are not the ones we should be using when we model heterostructures. Because as I showed you, in those heterostructures, we actually have a finite electric field. Or another way of thinking about it is that we've applied a constraint. Rather than having this freestanding layer where we just push on it, in the case of our heterostructures, there is a constraint that the in-plane lattice parameter is fixed to a certain value. And within the theory of piezoelectric polarization, this is perfectly straightforward to deal with, but you have to use different piezoelectric constants, the so-called improper piezoelectric constants. And this has not been done in the device simulations to date. All those simulations have incorrectly used the proper constants. And this second error has largely obscured the first error in choosing the correct reference structure. Just to kind of show you, again, we are talking about large differences between proper and improper. It actually depends on which constant you're talking about. The E33 constants are fine. The E31 constants are the ones that have large differences between the proper and improper value. And I'm telling you, we should be using the improper constants, which are very different from what is currently commonly used. Okay, so coming back to the full expression for the polarization, there is a spontaneous polarization contribution, there is a piezoelectric contribution. We have been using an incorrect reference for the spontaneous polarization, which actually leads to a large error. But we've also been using incorrect piezoelectric polarization constants, which kind of accidentally, that second error has largely canceled the first error. And hence the calculated values are not obviously all that different from the experimental values. Now, in my opinion, the fact that you make two errors doesn't make things okay. Okay, I would really prefer us to do things correctly. And you can wonder, well, I mean, if the values in the end are so close, why should we worry? Well, let me give you 4 reasons, and I'm sure there are more, why we should do the right thing, because this does matter. Okay, there are cases where these errors will actually not cancel so well and actually give you incorrect values. For instance, if you have large strains, people are very interested in InGaN with high indium content for red LEDs. The larger the strains are in these structures, which is going to happen at high indium content, the larger the error that you make. Okay, so not a good idea to do it incorrectly. If you have partially relaxed structures, the errors no longer cancel, and you should really be doing it correctly. And then there are the situations where you really are in a situation where you should be using the correct absolute value of the spontaneous polarization. Clearly, this is the case when you're dealing with ferroelectrics, because the zinc blend values for spontaneous polarization just do not make sense. But it's also the case if you want to look at interfaces between nitrides and nonpolar materials. And I know at Cornell, there is a lot of interest in those. For instance, gallium nitride, scandium nitride interfaces. Scandium nitride has 0 macroscopic polarization. It has a rock salt structure. You form an interface with Wurtzite, you're going to get the polarization discontinuity. You need to use the value reference to the layered hexagonal structure to correctly describe that. Okay. So I spent a long time discussing this part of the talk. How much time do I have left? I have a little bit more to talk about. It's much shorter than the first part, but please let me know how much time I have.
Professor, you have roughly 10 minutes.
Okay.
But we also have a question answer session, so we can enter that a bit as well.
Yeah, okay. So within these 10 minutes, let me tell you a second story, okay, which is also a story of like misinterpretation to a large extent in the field. And I want to take the opportunity of talking to an interested audience of trying to elucidate this. let me start out with giving you a bit of an intuitive view of where polarization comes from. And I want to do this in this sort of very simple picture, which is kind of a building block of the sort of chains of atoms that I showed you to schematize the Wurtzite structure. We have nitrogen, let's say gallium, nitrogen, gallium. This is a building block of the Wurtzite structure. We have the ionic charges on the nitrogen and the gallium, gallium 3+, nitrogen 5+, and then we have electrons, right? I told you in the zinc blende structure, these electrons don't play a role, but in the Wurtzite structure, they are what's going to give us the actual polarization. And one way to think about that in a simple manner is the way we often do when we think about bonding in a tetrahedrally coordinated material. We say, well, around the nitrogen and around the gallium, we have hybrid orbitals, sp3 hybrid orbitals, okay? And when you overlap these orbitals, you form 2 electron bonds. And in terms of counting electrons, for the gallium atom, for instance, since you have 3 valence electrons, each of these hybrid orbitals will contain 3/4 of an electron. For nitrogen, each orbital contains 5/4 of an electron. When you form a bond, you add 3/4 to 5/4 of an electron, you have a nice 2-electron bond, okay? And for the purposes of this little building block here and looking along the z-axis, I've tried to illustrate this filling of these hybrid orbitals by showing that on the gallium side, we have 3/4 of an electron in the bond, and on the nitrogen side, we have 5/4 of an electron in the bond. Okay. And if we didn't have to worry about polarization, this would essentially be the end of the story. This is a neutral building block. You can convince yourself that this would have 0 polarization, and you could just construct a Wurtzite structure by putting these building blocks together. Okay, so this is essentially a field-free situation, neutral dipole free. Now, we do have polarization, and a simplistic but actually correct way of thinking about that is that the electron cloud has slightly shifted. I talked about these electrons sitting in these hybrid orbitals, okay? I'm going to tell you that we can think of polarization in a material like gallium nitride as the electron cloud shifting slightly to the left. Now, in the interior of our material, this will not make any difference because, sure, everything shifts a little bit to the left, but we're still going to have good 2-electron bonds. But at the surfaces of our little building block here, it does make a difference because now our electrons in our nitrogen dangling bond, so to speak, have shifted a bit to the left, and also the electrons in the gallium dangling bond have shifted a little bit to the left. But overall, this is still a neutral and dipole-free building block. Okay. So I'm going to use this simple picture to talk about the origin of carriers at an interface between gallium nitride and, for simplicity, I'll say aluminum nitride. I told you in the beginning, you have a polarization discontinuity that sets up a bound charge at the interface, you get electric fields, and ultimately this gives you a 2-dimensional electron gas. Okay. Now, over the years, people have spent a lot of words discussing where the electrons in that two-dimensional electron gas come from. If this were gallium arsenide, aluminum arsenide, we would need to add intentional doping to get electrons at the interface. But in the nitrides, we don't need to do that. People have explicitly checked this, that you do not need doping, explicit doping anywhere in the structure to get this two-dimensional electron gas, okay? It's also been verified that even if there is unintentional doping, the number of electrons that you get is not large enough to explain the two-dimensional electron gas. So what people have kind of settled on is that these electrons come from surface states. In a structure like this, the aluminum nitride has a finite, usually very small thickness, only a few nanometers. It's terminated at a surface that is still relatively close to the interface. Surfaces have surface states, and it has been postulated that these surface states are donor-like and hence supply electrons that go into the two-dimensional electron gas. However, starting some years ago already, including in work done at Cornell, it was pointed out that there is a problem with this way of looking at things, namely the density of surface states is not high enough to be consistent with this explanation. The density of electrons in the two-dimensional electron gas can be, I'm just saying something, close to 1 times 10 to the 13th per square centimeter. In good material structures, the density of surface states is much less. So if you don't have enough surface states, how can you explain the origin of these electrons? What I'm going to try and tell you, and I'm just inviting you to think about it in more detail later, is that we do not need to worry about where these electrons come from, because essentially their origin is intrinsic. They are given to us for free. Where are they coming from? This is the picture that I showed you for gallium nitride. We are interested in an interface. So we are bringing in aluminum nitride, and I'm only focusing on what's happening right at the interface. And we can see that at the interface, of course, a bond will form, and we will have a polarization discontinuity. Now, I told you before how to accurately calculate that polarization discontinuity, because we have accurate values for the polarization of gallium nitride, accurate values for the polarization of aluminum nitride. If you use those correctly referenced values, you're going to find that there is a positive polarization discontinuity, okay? And hence we know that there will want to be electrons at this interface that kind of compensate that positive charge. The question is, where do these electrons come from? And within the picture I was sketching for you, they come with the structure, because to explain the polarization in gallium nitride, we shifted the electron cloud a little bit to the left. To explain the polarization in aluminum nitride, you need to shift the electron cloud a little bit more to the left. And so at the interface, we end up with an excess of electrons over and above the 2 electrons that we need to form a bond. And all these electrons can do is go into the conduction band. This is where these electrons come from, okay? So they arise because of the shift in electron clouds that is intimately associated with the origin of the polarization. Now, once you adopt this picture as your starting point, the question you need to ask is not so much where do the electrons come from. The question you should be asking yourselves, and we should be asking this as theorists, but also as experimentalists, how do we keep these electrons at the interface? We want our 2-deck density to be as high as possible, but some of these electrons may want to leak away to surface states. This is where the surface states come in. The surface states are not the source of the electrons. They are basically a sink for electrons. If you have surface states, they will drain away some of these electrons that in principle could be present in a density as high as the polarization discontinuity, but some of them will drain away to the surface, and preventing them from draining away will enhance the 2-deck density, okay? And in order to address that, you need to worry about the structure of the surface. There is compensation charge on the surface, bound charge, etc. We addressed all of this in this paper here, which I'm not going to go into, except to say that what I was telling you isn't just, again, me waving my hands. We did explicit first principles calculations for interfaces between gallium nitride and aluminum nitride. We explicitly see these electrons piling up at the interface. This is definitely a real effect that was described in this paper. What I'm going to end with is to say that very revealingly, in the process of doing this work, we found a paper by the group of Grace Ching and Daptip Jena from 2011, in which, using somewhat different words, they essentially confirmed the picture that I was describing, namely that you need to think about this whole picture in terms of bound charge, fixed charge being present at the surface that's going to keep the electrons at the interface. And actually the values that were extracted from experiments at that time agree virtually perfectly with all the calculations that we've done. So I'm going to end here. I hope I've told you some modestly interesting things about the sign and magnitude of spontaneous polarization, and given you an intuitive view of polarization that can give you insight into the origin of electrons at the interface. And I'm sorry for going over time, but I'm happy to stay around to answer any questions you may have. Thank you.